All right, people. We're doing discrete data. This is 4.4, graphing a function rule. Function rule. We're graphing a function rule. We will be in the ocean today. Look at the ocean. Ooh, it's a coral reef. Ugh. All right, we're in the ocean today. That's where we're at. All right, so that's the name of this. It's called ocean. Y'all see that? It's ocean. This is bronze. This is lava. You already know what's my favorite, but you can't see it. All right. So anyway, discrete data. Discrete data is represented on a coordinate grid by graphing points, but not connecting them with line segments. A discrete function is used to represent data that has holes. Let's underline that word right there. Has holes. That is functions where only the values of certain points make sense. Only the values of certain points make sense. Now, y'all, we seen discrete data. We seen discrete data when we were asked to find the domain of different word problems. And we were like, hey, it doesn't make sense to break this up into anything other than integers. Integers are whole numbers and their opposites, because we can't have a half of something. So, for example, it says the number of people attending the movies, number of cartons of eggs bought at a store, the amount of money made from selling packages of cheese are all examples of discrete data, because you can't have 3.5 people go to the movies. You can't buy 5 3/4 cartons of eggs. Okay, you can buy 2.5 dozen of eggs in one carton. You can't what's this? You can't buy 4 2/10 packages of cheese. You can buy 4 2/10 pounds of cheese, but not packages. So therefore, this data only makes sense for certain point values. So the key word right here it's called discrete data, but we're talking about, where's this word at? It's not in here. Oh, I just teach it. Oh, we're talking about distinct points. Yes, write that down. Distinct points. That is what we're talking about. We're talking about distinct points, meaning that they are distinguished. They don't look like everybody else. So they stand out. And they stand out because they're not connected. All right. So this example says the cost D in dollars for a parking pass depends on the number of whole weeks W you purchased. This situation is represented by the function rule D is equal to 25W. So we know a function rule. No, maybe you don't know this. I think I've emphasized this. I don't know in which class. But a function rule is a fancy way of saying an equation. And that's what a function rule is. It's basically an equation. When you see the function rule, you see D is equal to 25W. If you see an equal sign, you know you have an equation. All right. So we need to represent this data. And so we ask ourselves in this problem, what would be an appropriate domain? What number should we start off with? So if W is weeks and that's our domain, we know it's our domain because it's our input right there. If that's weeks, then an appropriate domain would be to start at what? 0, like you said. If I don't go any weeks, if I don't use my parking pass for any weeks, that means I paid $0. All right. If I use my parking pass for 1 week, I pay $25. If I use it for 2 weeks, I pay $50. 3 weeks, I pay $75. And then 4 weeks, I pay $100. Whoa, that looks a mess. All right, let me just delete this bad boy right there and put this 100 in here. 100. All right, so that's that. So we're going to have to plot this. So I don't know why I have this down here, but I do. It's out of order, but whatever, it's here. So creating a complete graph, remember the 7. The first thing we need is a title. The second is the x-axis labeled, the y-axis labeled. The fourth, I said the second, I said 2 things, but the fourth thing is the independent variable correctly identified and labeled on the x-axis. The fifth thing is the dependent variable correctly identified and labeled on the y-axis. Number 6, a numbering scale for the x-axis appropriate for the data range, starting with 0 at the origin and using in equal intervals. And then 7 is a numbering scale for the y. All right, it's the same thing. Okay, so when we come up here and we're going to label our name our graph, we look at the situation. What are we talking about? We're talking about the cost of parking passes. So we can say the data, the name of this graph is the cost of parking passes. Y'all see the ocean? That's the ocean. Ooh, we're going swimming. All right, the cost of parking passes. All right, so they said that we have to have the y-axis and the x-axis labeled. So we're going to label this the x-axis. Sometimes you'll see a W there, and then you won't see a y. You'll see whatever the variable that we're using for the range. You'll see a D. All right, and then they want us to appropriately label the y-axis. So what is the y-axis? What is our output? Our output is our D, which is our dollars. So we're going to label this dollars. And our x-axis labeled is W for weeks. And I'm putting it down here because I have little space down here because we're going to have to pick what? Appropriate intervals. Okay? And that is, let's see, we got the title, check. X and Y axis label, independent variable identified. Yep, identify. Now we now have to pick a numbering scale for the X and the Y axis. So when we come up here and do a numbering scale, let's look at the range of our numbers so we can use the graph appropriately. So on our domain or our X values, the range of numbers, they range from 0 to 4. Now notice we have 0, 1, 2, 3, 4. If you graph all your data within this line, I'm going to say you're wrong. Get out of my face. All right? I might just say get out of my face, dude. It depends on how I feel, you know. All right, so don't do that. So we have this whole graph here. So we're going to break this graph up so that we can represent this graph. So I already counted this. There are 15 lines here. So I have 4 of them in the graph. If I have 15, if I get 5, then I'll have enough room to graph this. So in order to get 5, 15 divided by 5 is 3. So we're going to go by 3. So every 3, we're going to say that's 1, that's 2, that's 3, that's 4, and that's 5. All right, so what is this graph going by? Thirds. That's what it's going by. Thirds. Okay? And then when we look here, this is 15 on the y-axis as well. We have to go up to 100. So if we take 100 divided by 15 and we get like 6, but who want to go up by 6 each time? That don't make any sense. All right, and we can't go by 5 because we're never going to reach 100. So let's go by, actually 100 divided by 15 is 6.6, but nobody's going to do that. So we're going to go by 10s. So I'm going to skip this because I'm running out of room. So if I go by 10s, I let this be 20, 40, 60, 80. And I'm only doing that because of space. And I just want to not write everything. And then that's 90 and that's 110. All right, so now let's graph. So we have 0, 0. Right here we have, let me get my little cheat tool. Y'all ain't ready. Y'all ain't ready. Y'all not ready. I know y'all not ready. Y'all just don't know you're not ready. Woo! Look at that. 0, 0. 125. Well, that's 30, Mr. O'Neil. So 25. The dot got to lose some weight, y'all. It's taking up too much. That first dot can be that big. This other dot got to lose a weight. All right. So 125. Right. Come on, buddy. Right there. Oh, gosh. It's like Daddy Dot. This is Baby Dot. Hey, Baby Dot. All right. We'll call this Dot Sadu so he can feel special. Look at little Sadu. All right, little Sadu. All right, 250. All right, we'll call this Dot 50. That's 50. Little Emma. Look at little Emma. Look at her. Oh, cute. 375. Hold up. Where's 75? Okay, that's 70. And this 75. We'll call this Dot Little Mariah. Look at little Mariah. All right. And then for 100. Ooh, I'm tired. For 100. Is that 100? That's 110, Mr. Odell. This is 100 right here. For 100. All right. And we'll call that. Let's end with a big bang. Let's end with a bang. All right. Get a little fatness, a little thickness. We don't want to say fat. People might be offended with the word fat. You know, we live in an offense generation. All right. And we'll call that dot. Who can be this dot? Let's call this dot Jackson. Look at Jackson. Look at Jackson. So we started with Sadu and we ended with Jackson. Y'all know they're BFFs, right? You know they're best friends. All right, shout out to you. So why is this? It says, why is this discrete? Well, the reason why this is discrete because there is a key word in our sentence that we were given. It said whole weeks. Now this is supposed to be an underline, but whatever. So we can't have a half a week. We can't have a quarter of a week. We can't say 3 days. No, this says break this up in whole weeks. So if these are whole weeks, these lines should not be connected. Do, write this, not connect. I just went into the ocean, y'all. Y'all see me swimming. All right, do not connect. All right, that's 11 minutes on that one problem. Whew, gosh. Y'all gonna have a long video. I feel y'all. Good. Y'all be watching for a while. All right, continuous data is represented on a coordinate grid by graphing points and then connecting. You connect the points. Oh, we got to go back to the ocean. Just hopped out of the ocean. Connect the points with the line segments. In many situations, it is also appropriate to place arrows. Some situations, appropriate to place. Y'all, when I say appropriate, I don't know why. It just sounds funny to me. All right. To place arrows on both ends of the segment to show that the possible solutions continue indefinitely. Ooh, look at that. Infinity. Examples. Distance covered over time. Amounts of gas remaining in your gas tank. Area of a square based on the side length. Cost of an item sold by weight. So think about this. This stuff is fluid. I call it fluid. That means it's constantly connected. All right. So when you think about distance over time, when you're traveling, you're like, I'm traveling. You don't skip and be like, ooh. That would be, magical. Because you stopped and you ended up somewhere else. That's teleportation. Even though you teleport, you still have to travel. So, but whatever. We're not going to get into the science of this. But you can't do that. When you think about your gas and your gas tank, you might start here. The gas may be up here, but as you drive, it goes down. You don't stop and be like, ooh, I'm going to go down and I'm going to go down here. You don't do that. All the people that's making the lines like this, I'm proud of you because you really don't have to do this. Hopefully nobody is doing that. All right. And the area of, Nico might be making the lines. All right, Nico, I'm proud of you. Area of a square base on the, whatever. Y'all get the point. It's connected. All right. So the price P in dollars for apples depends on the weight W in pounds of apples. This situation is represented by the function rule P is equal to 1.50. 1.50, Jesus. 1.50 W. What? Yeah, 150 W. All right. So when we look at this, we know our domain is W and our range is P. Our input is W. Our output is P. Y'all, I'm not going to go through label. I guess I should. Never mind. Well, just never mind. All right. So an appropriate domain to start will be 0. If I don't buy any apples, I pay no money. Yoo-hoo. If I buy 1 apple, I pay $1.50. If I buy 2 apples, I pay $3. If I buy 3 apples, I pay $4.50. And 4 apples is $6. All right. So there are 15 lines again. Notice we have to go 1, 2, 3, 4. So we know that that's what we're going to go by. And then it goes from 0 to 6. All right. So, and it's like 1.5 in between. So if there's 6 here and we know there's 15 here, we can technically go by halves. So every half is 1. So that'll be 1. That'll be 2. That'll be 3, 4. All right, I'm not going through and graphing this. I want y'all to do this. So what would be the name of this? Cost of apples. All right. What will we name this? The Y would be the pounds. Yeah. I thought I did that wrong when I was looking. And then what would be the X? That's Y. X would be the weeks. And we set up the weeks like we did last time. We go every 3. All right. And then I want y'all to graph this. And so pause the video now and just finish graphing that. Okay. Do that. And after you graph it, it says, is this graph discrete or continuous? Well, y'all, please don't. Somebody in the class did not graph it and you stop there. Don't do that to your life, because I'm going to ask who would do that. Chris Wilson. Chris Wilson, you hear me. You hear me good. Don't you sit there and don't graph this thing. I'm just going to do it when I get home. Chris Wilson, you're going to forget. All right, that's enough. Okay, so discrete or continuous? Well, we're talking about pounds here. So you can have a half a pound, you can have 3/4 of a pound, you can have 2/5 of a pound, you can have 3 pounds and 2 ounces. So we can connect these dots. So it's going to be a line that goes up like that, and we can put an arrow at the end. Honestly, now this won't go on. It can theoretically go on indefinitely, because you can keep adding apples until infinity happens for eternity. But yeah, we're just not going to do that. All right, let's move on. Got that done. Let's get to this. All right, so this is something that you're going to do on your own. You know what? I might not give y'all that homework. I might let this be your homework. Wouldn't you like for this just to be your homework and I don't tell y'all the graph? I don't know. I might change my mind when I move down there. So it says classify the data as discrete or continuous. Explain your reasoning and sketch the graph of each situation. Your weight from birth to now. So you're going to make something that looks like this. And this is your title. And then you're going to label your X. You're going to put your little tick marks here. You're going to put what your X and your Y. You're going to have your tick marks here. And you're going to think of your intervals, and you're going to talk about, is this continuous or it's discrete? And you're going to do that. Your weight from birth to now. All right. And then over here, it says the time you get up each morning for 1 week. So you're going to do the same thing. You're going to make a graph. This is your title, so you don't have to title anything and break it up as such. This is going to be homework. All right. Look at me being nice. I might just take some problems out of y'all homework, because this is what I'm letting to be homework. All right. Well, you look here. Okay, so yeah, I'm gonna do that because I'm not gonna want to do all of this, because this video is gonna be super long if I do all these problems, and I'm just not. So this is gonna be something y'all gonna complete. All right, so I'm getting rid of your homework. Yay! That means y'all don't need graphing paper. Yay! When you graph a rule, make a table. Use at least 5 values to get a sense of how the graph is forming. Use 2 positive, 2 negative, and 0. If there are fractions in the problem, use numbers divisible by the denominator, so you will end with integers. So let me explain this. All right. So you don't have to write this, just watch. So when you're graphing, I always use these points. Actually, do write this down. Write these down. Use these points. These are our given values. I said 2 positive, 2 negative, and then 0. I use the easiest 2 negative numbers, which would be -2 and -1. And then I go to 0, and then I graph 1 and 2. So the only time I don't use those 5 values are when I have a fraction, because those values sometimes will give me decimals, and I don't want decimals. I want to graph integers. So I use numbers divisible by the denominator, which you will see. Y'all see the ocean over here. Okay, so you'll see that in a second. So I always use those values so as my input to find my output. Now, don't write this. The reason why I do that is because I want to see how the graph is changing over time. That's what I want to do. I want to do what happens when the graph is over here in the negative land. And then this highlighter leaves it. Come on, go on a little diet, buddy. Go on a little diet. You're doing too much. All right. And then what happens when the graph touches 0? And then what happens when the graph come over here in the positive land? Sometimes there are different things happening across the x-axis. So that is the reason why I use these values, because I want to see how the graph changes over time. That might just be a question on the quiz. I don't know. It just might happen to your life. All right, so let's get it. So here is my x value. You're writing with me. Then you write the function rule here. I don't put y equals 2x squared for the sake of space, so I just put 2x squared because that's what I say that I'm inputting my x into, and then whatever I get left over is my y. Now y'all did this in this the linear and nonlinear sort, but we're doing our own now. So we have -2, -1, 0, 1, and 2. Now I'm going to do the first couple for the sake of time in the video, and you're going to finish the rest for homework, and then we're going to use this as our homework instead of the 6 problems that I'm going to have y'all graph after this video. You're welcome. Yep, you're welcome. You're welcome. You are so welcome, Peter. You're so welcome, Ben. You're so welcome, Melvin. You're so welcome. So welcome, Katie. All right, so we have, some of y'all are doing this wrong. You're supposed to do the order operations. The order operation says that you must square this and then multiply by 2. Y'all remember PEMDAS? P-E-M-D-A-S. PEMDAS. All right, so you square the -2, which is going to give you 4, and then you multiply that by 2, and that's going to give you 8. You square the -1, that's going to give you 1, and you multiply that by 2, and that's going to give you 2. You square the 0, and that's going to give you 0, and you multiply that by 2, and that's going to give you 0. You square the 1, and that's going to give you 1, and multiply that by 2, it's going to give you 2. Square the 2, that's going to give you 4, and multiply that by 4, multiply 2 by 4, and that's going to give you 8. So I did all the hard work for y'all. I just need y'all to graph it. All right, that's what I need from you. You come over here and you graph that, and then you tell me. This is called a quadratic function. Ooh, I might do some extra credit if you remember what that, when x is squared, is a quadratic function. Ooh, about 3 months, 4 months from now, we're gonna be doing a lot of that. All right, let's come over here. Notice that we have a fraction. What did I do? What did I say? I said this: if you have a fraction, you want to choose numbers divisible by the denominator, because if you choose -2, -1, 0, 1, and 2, when you do -2 times 1/3, don't write this down, but -2 times 1/3 is going to give you -2/3. Who want to graph this? Anybody trying to graph that? No, we're not going to graph that. So what we're going to do, we're going to choose numbers divisible by 3. So what will be our -2 version of a number divisible by 3? Okay, I'm gonna let y'all think. It's basically what's the second smallest negative number divisible by 3. That number is -6. So -6 will go here, and then -3 will go here, and then 0, and then 3, and then 6. If you're asking why, come on, y'all. I'm 2 places away. You can just say, hey, 3 times 2, 6. And then I'm 1 place away from 0. So I'm looking, if you look at this like a number line, look at this like a number line. So if I go 2 places away from 0, 2 places away from 0 is right there. That's going to be -6. All right, so let's plug these in. So we have x, 1/3 x, and then y. So if I take 1/3 of -6, that's going to give me -2. If I take 1/3 of -3, that's going to give me -1. If I take 1/3 of 0, that's going to give me 0. If I take 1/3 of 3, that's going to give me 1. That looks like a B, but it's a 3. Who would ask that? Nick. That's a 3, Nick. That's a 3. If I take 1/3 of 6, that looks like a G, but it's a 6. Cammy, Hukami, that's a 6. That's 2. All right. So yes, you're going to graph these on the same graph. What do you mean? I mean that you're going to graph them on the same graph. What am I graphing? You're graphing the order pair. I can hear Nick asking, what am I graphing? You're graphing the order pair. So this -2, 8, -1, 2, 0, 0, 1, 2, 2, 8, -6, -2, -3, -1, 0, 0, 3, 1, 6, 2. That's what you're graphing. I'm a beast, y'all. I wish y'all can get on my level. You will surpass my level. You know, I wish you're gonna surpass me. Oh God. Who cares? All right, so we have these other problems to graph. This video is going to probably be like 35 at the most minutes long. I spared y'all by giving you the homework away. So, and I did the last problem. So I'm going to set these up. Y'all going to finish the rest because I ain't got time. All right, so literally, I got to make another video for y'all right after this. So we got an x. We got our function rule is take the square root, not the square root, the absolute value of x plus 2. And it's going to give us our output of y. What values do we use? Well, since we don't have any fractions, we're going to use our given values, our go-to values, -2, -1, 0, 1, and 2. So, the absolute value is how far away a number is from 0. So the reason why the absolute value is never negative is because you can't be a negative distance away from anything. All right? So the absolute value, you don't have to write this down, is how far a number is away from 0. So if I have -3 here and +3, -3, -3, -3 is 3 units away from 0, so it's 3. So that's why it's always positive. Distance can never be negative. You know, that sounds like a good question to put on a quiz or something. It really does. It really does sound like a good question. Distance can never be negative. Distance, distance, distance. Christopher M. Distance can never be negative. Christian, distance can never be negative. Yeah. Jasmine, distance can never be negative. All right, so when we take the square root of -2 and add 2 to it, basically the square root of -2 is 2, and 2 plus 2 is 4. All right, we take the square root of -1 and add 2. Usually I make these darker because if I don't, and I know it looks a mess right here, but if you don't, some people think it's 1 minus 21 plus 2, and you get mixed up. That looks like Phoenix's handwriting. No, it really looks like Chris Bullard's handwriting. You know, he's having a fit because I said his name. All right, so we get -1, square root of -1. Remember Chris Wilson, we're looking at Chris's handwriting. Yeah. The square root of -1 is 1 plus 2, which is 3. The square root of 0, not the square root, the absolute value of 0. Goodness gracious. The absolute value of 0 plus 2. 0 is 0 away from 0, so that's 0. So 0 plus 2 is 2. The absolute value of 1, this looks a mess, plus 2 is 3. The absolute value of 2 plus 2 is 4. Okay? All right. So when you graph this, because you're going to graph this on your own, instead, I know we're used to making a U, but this makes a V. This makes a V. So when you graph this, make sure you put arrows at the end, and you're going to make a V. The absolute value makes a V. All right. So what I want you to do, you're going to do the middle one on your own because it's pretty simple. You're just cubing the number, and I'm not going to go through that. You know, you're going to pick -2, -1, 0, I mean, all that good stuff. You're going to do that. That's homework. 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 And then you're going to come over here, and you're going to put the absolute value of x minus 1. And then you're going to get your y. And then you're going to use your -2 all the way down. And I'm going to do the first one with you because some of y'all need this. And I'm not throwing shade, but it's just like, I don't want y'all to make a mistake. So if I take the absolute value of -2 minus 1, and we treat this, the absolute value bars like that, the parentheses. Y'all see the ocean? The ocean is there. And so you do what's inside. So -2 minus 1 is -3. -3 is 3 units away from the 0, or from 0. All right. And then you graph those, and that's what you're going to finish for homework. So, wow, I made this video less than 30 minutes. Is there more? And there's no more. Mr. O'Neal is being nice to these kids. You know why? Because I'm the greatest. It's time to put on some weight, buddy. I'm the greatest. This has been another Beast Mode production. It's been great that you watched this. Hopefully you can do your homework. It shouldn't be that hard. It's really not that hard. All right, have a great life. Goodbye.